Okay, question 6. Question 6 is your charges. It is pretty simple. So the first question asks you what will happen when the switch is closed. Now when the switch is closed, the electron from the sphere L will move to the positive terminal of the supply. Okay, because unlike charge attract. So what you need to describe here is quite straightforward. Just say that the electron in L will be attracted to the positive terminal. Down here you may want to add in because unlike charged attracts. Okay, so as a result, L will be positively charged because it loses electron. This is very important as well. Okay, then after that, describe what is the effect on the conducting sphere S. Okay, for your part B. For your part B, what happens is that induction will happen. So this guy here become positive. So what happens is that this positive charged sphere L will have an electric field all around it, and because of that, the conducting sphere S will be induced, and an induced negative charge will be on the left, and an induced positive charge will be on the right. So what happens is that the electron in the sphere S will be induced to the left hand side, and so as a result, negative charge is induced on the left hand side of S, and since unlike charge attracts, S will now move towards L. Okay, simple as that. Now you are asked to label all the forces. This one you have to be careful because they say all the forces. So whenever you label forces, the number one force that you should come to your mind is that what? It is on Earth. Yes, there will be a weight. Because there's a thread here, there will also be tension. Okay, and this one, positive, negative. Please, when you are drawing this tension and weight, they should be around the same height to show that they are in balance. Okay, then because unlike charge attracts, so then therefore there will be a force going this way. This is the F. Okay, and but don't forget you have induced positive charge here and positive charge here, so there will also be a force here. So let's call this repulsive force, this is attractive force. Now why is it that attractive force is larger than the repelling force? Why is it that this one will be stronger? Good, yes, it is because the charges here are slightly closer to this sphere. So the the force due to the electric field depends on the distance. Okay, so therefore this distance is nearer to this, so therefore this force will be stronger than this force, which is further away. Okay, the forces generated by electric field depends on two things: the distance between the two charge and how strong the charge is. Okay, so in this case we are looking at the distance. Okay, so that's all. You should have 4 forces. So now they ask when sphere S is connected to the Earth, what is the effect? So what happens is that S is connected to Earth. Now it doesn't matter where you connect your Earth wire. It doesn't matter whether you connect it on top, below, on the left, on the right. Why? Because sphere S is conducting, meaning that the electrons can move freely inside sphere S. So no matter where you connect your Earth wire, it is the same. Okay, some of you ask me, where is the Earth wire connected to? Anywhere on S, it doesn't matter. So what will happen when you connect it to S? So due to the induced positive charges on S, electrons from the Earth will move towards the S, okay, and neutralize the whatever that is being induced on one side. Okay, this means that S will now have more electron than the positive charges. So therefore, S will become negatively charged. Okay, the idea is the electrons from the Earth will move towards the induced positive charge. And as a result, S will now carry more electrons than the positive charge. So therefore, S becomes negatively charged. Now, in terms of position, if now S acquire more electrons from the Earth, that means the force of attraction towards the positive charge here will be stronger because now S carries more electrons. So just now I mentioned that the forces due to electric field depends on number one, distance, number two, the amount of charges. So now S actually have more charges now because of the earth wire, then the forces of attraction will be even more, okay, because now more electrons. So therefore it will move further towards L. Okay, and since the question only asks you to describe the effect, you do not need to explain. You just need to tell them that, okay, now the deflection towards L will be greater. Okay, question 7. Question 7. First question they ask you is that what will be the direction of deflection? Now, take note, this is positively charged. And when you talk about deflection, you have to use your left hand rule. Okay, you have to use your left hand. So, force, FBI, right? Force, B field, the magnetic field, and the current. So this current is actually the conventional current. Conventional current meaning that you are actually imagining that the positive charge is moving. So this is positive charge and it's going from left to right. So therefore your middle finger should be left to right. And this is the field, the magnetic field is going into the paper. So your index finger go into the paper. So middle finger left to right, index finger into the paper. So therefore you would have an upward force. So you would know that the deflection will be upward. So write it down. And you will get your 1 mark. Okay. Then after that, you have another setup. So you have two parallel plates. In between is vacuum. Okay. And this time you have electron. And when you have electron moving, this is true electron path. Meaning that the conventional current, which is actually described by a positive charge, the conventional current will be this way. Okay, if you are not clear what I'm talking about between conventional current and electron movement, read your textbook on DC circuit. Go to the index page, search for conventional current. If you still have difficulty, come look for me. Okay, to cut things short, it's very simple. True electron flow will always be from negative to positive because electron is negative, right? And light charge repel. So true electron flow is going from negative to positive. But if you look at a lot of your circuit diagram, it is the current is moving from positive to negative. So what happened is that we call this conventional current. Why? Because last time when scientists are studying electricity, they thought that what is moving is the positive charge. Only later then they find out that what is moving is the electrons and not the positive charge. So in order not to create too much confusion in the non-scientist community, they call this conventional current. That means they let it be. Okay, that means they let engineers and all that think that, okay, current is from positive to negative. It is a convention whereby everyone is already comfortable with. So conventional current is from positive terminal to negative terminal. So when you are having this kind of thing, path of an electron, it is true electron flow. And the conventional current, which is being used on your left-hand rule uses conventional current. So because of that, you need to be able to identify that, okay, when true electron flow is from left to right, then conventional current is from right to left. So your FBI, your middle finger, need to go to the left. Okay, and this is what? Is this? Oh, this is just a terminal. Oh, okay. Sorry. I thought this is a magnetic field. So this is just an electric field. If this is an electric field, then it's even more easier. You don't need to talk. You don't need to care about conventional current. Okay, you just take that as additional information. Okay, I'm sorry to confuse you. And I'm too lazy to make a new video because of this blooper. So this electron is negatively charged, right? And negatively charged will be attracted to the positive terminal, meaning that this path will go this way. Yeah? Okay, draw the line to represent the electric field between this plate. It is very easy. Electric field will always be straight. Okay, but be very careful. You want it to spread out equally. So I'm using the lines here to make sure that it goes this way, this way, this way. And at the edge, it will be slightly bulged out. Oh, okay. So down here, I will also draw it. Bulge out. Okay, and direction is always from positive to negative. So this is my electric field. Okay, then after that, show the path of the charged particle between. Okay, so then the path will be like that. 2 marks, just like that. Okay, electron is accelerated from rest through the potential difference of 750, blah 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 blah. Okay, let's see what is in store for us. Okay, for part 1. For part 1, you are asked to find the change in electric potential energy. So when you are talking about the change in potential energy, what you can do is that they already tell you that the potential difference between the two plates is 750. So the change will be the work done. So just put in the values into this equation, you will get the change in electrical potential energy, which basically will be converted into the work done. Okay, then after that, find the final speed. So the electrical potential energy will be converted into your kinetic energy. So just equate into half mv squared, you will be able to find the velocity of the electron.